There we go. So, just to remind you, we've got, so far, we were talking about the pituitary gland as a whole, okay? There's two parts, right? The anterior pituitary, okay, and the posterior pituitary. But we are focusing now on the anterior portion, right here. Okay, it is connected to the hypothalamus. In the hypothalamus, you have cells, neuroendocrine cells, shown here, yellow. It's like neurons, okay? So they produce hypothalamic hormones, which then enter the circulation. That's primary plexus. Okay, they enter primary plexus, and then via hypothalamic hypophyseal portal system. Let me erase it. And so this is going to be your portal system, okay, to not to blood vessels, okay? When you see portal system, it's blood vessels. Through the portal system, those hypothalamic hormones reach secondary plexus. This time in the anterior pituitary. Okay? Then hypothalamic hormones stimulate the anterior pituitary. And whatever hormones they trigger, anterior pituitary produces, and I want to highlight this word, produces and releases into the general circulation. So far, we good? And then we also mentioned that many actually, of the hypothalamic and pituitary hormones are parts of so-called hormonal axis. Like axis that involves stimulation of thyroid hormone or adrenal hormones or gonadal hormones. Okay? Good? Can we move on? The hormone that sort of ends in the anterior pituitary, if I may say so, is a growth hormone. It's probably the most important. Well, no, I wouldn't say the most important, but when you say pituitary gland, the first thing that comes to mind is a growth hormone. Guess what? It stimulates growth. Now, growth hormone is stimulated by another hormone. Okay, now let's take a glance. So you have hypothalamus. Hypothalamus produces growth hormone releasing hormone, GHRH. It's a tongue breaker. Okay? So you have GHRH, which then stimulates the production of growth hormone. Here you are, in the anterior pituitary. Growth hormone has direct and indirect effects. The direct effects of growth hormone are, sorry about that, the increase in fat breakdown and elevation of blood glucose. Okay? To understand why these effects are taking place, what is the role of glucose in the human body? Yeah, exactly. It's a source of energy, right? Now, when we say fat breakdown, fat triglycerides, they can be metabolized by themselves. They have to be broken down into glycerol and free fatty acids. But what is a main role of fat in the human body? Not so much. Energy storage. Again, it comes down to energy. Does that make sense? So essentially, elevated fat metabolism and elevation of the blood glucose is the meaning to provide human organism energy sources. Does it make sense? Because to grow, you gotta have an energy. Make sense? Indirect effects involve protein synthesis, which results, now think about this. What I love about endocrine system, you just think it through. It is logical. You've got growth, which requires energy. Energy will come from glucose, which growth hormone will bump up, and free fatty acids, for instance, which will come from lipids. Now, growth, why cells grow? How do they grow? They produce more proteins. They become bigger, essentially. Okay? So that's your elevated protein synthesis and cell growth and reproduction. Cell growth and reproduction results in the more bones. Well, not number-wise, but weight-wise. You still have the same 206. They're just bigger. And muscle growth. Does that make sense? Now, muscles will not necessarily, well, skeletal muscles, they will not grow because of the cell division. Cells will just become bigger. So again, direct effects are associated with energy. They're metabolic. Indirect effects are promoting growth. Okay? So far, are we clear about distinction between direct and indirect? Any questions? Why indirect effects are called indirect? Because the axis that leads to the indirect effects involves another hormone. Look at this. Growth hormone acts first on the liver. Liver produces so-called insulin-like growth factors, or IGFs. Insulin-like growth factors, in turn, will stimulate protein synthesis, bone growth, and blah, 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 and cell proliferation. Does that make sense? So it's not growth hormone that immediately has an effect. Growth hormone stimulates IGFs, and IGFs will then, elicit the effects. Does that make sense? Now, so far, imagine that you have growth hormone releasing hormone, right here, in the hypothalamus. It will stimulate growth hormone. Growth hormone will stimulate IGFs. IGFs will stimulate growth. What's going to happen to a human body if it's just going to go and go and go and go? What's going to happen to us? Huh? Yeah, we're going to keep growing. We also will run out of what? Fuel, right? Fat and all potential sources of glucose, right? We can just keep growing. It's got to be limited, correct? So, these insulin-like growth factors will act as the regulators by negative feedback on the growth hormone and on the hypothalamic hormones. Okay? So, IGFs will inhibit growth hormone. They will inhibit growth hormone releasing hormone, but they will stimulate growth hormone inhibiting hormone. Does it make sense? Now, let's take a little sort of a mental experiment. Imagine that you have a patient and you inject the patient with a growth hormone. Then in a time progression. You inject growth hormone and you start measuring insulin-like growth factors. What you're going to see? They'll increase. Very good. Pretty much the entire endocrine system is about increase, decrease, increase, decrease. Okay? So IGFs are going to increase. What's going to happen next? So GHRH will go down, growth hormone will go down, and GHIH will go up. Does that make sense? What we've just done, you have to, for this topic, for endocrine system, you have to think in increase-decrease terms. It's all about going up and going down. Am I clear? Really, because a lot of questions, the majority of physiology questions that I'm going to ask in the exam will be, if you change the level of this hormone, like if you increase this, what's going to happen? And I give you several options, and you pick the right option. Am I clear? So, and since I don't limit the time, you can picture those axes. And you know, it's really easy in the end. Because you picture this, regulatory axis. Okay, crosses are, so this is inhibition, okay. So you picture this and say, okay, if I bump up IGFs, growth hormone will go down. Does that make sense? It's all about drawing those flowcharts. Now, this just shows you the effects, the gross effects of exogenous growth hormone. Now, that's another set of words that you got to get used to. What is the difference between exogenous and endogenous? Exo versus endo. Endo means inside. Exo means outside. Exogenous, genus part, refers to generation, where it comes from. So exogenous comes from outside. Endogenous comes from the inside. Endogenous hormone is the one that you produce. Does that make sense? Exogenous is the one that you shouldn't. For people with type 1 diabetes, insulin that they take is exogenous insulin. Okay? Now, you take rats, which are pretty cute animals and very smart. So you take like half-pound rat, white rat, and you start injecting growth hormone. They become ginormous, more than a pound, huge monsters. Okay? Because growth hormone will promote the growth of, cartilage and therefore skeleton and muscles and whatnot. Does that make sense? Now, what stimulates the growth hormone? Some things are easy to remember. Others, you just have to think about the effects. If something changes in homeostatic parameters, what is hormone supposed to do with that change? Bring it back to, correct. Bring it back to normal, right? So, growth hormone can increase blood glucose. What will stimulate the release of growth hormone then? If it increases glucose in the blood, what can stimulate growth hormone release? Low blood sugar. If it increases free fatty acids, if it breaks down triglycerides to free fatty acids, what can stimulate the release of growth hormone? Low free fatty acids. Does that make sense? So that we kind of can cross it out. Okay, decreased blood glucose, decreased blood free fatty acids. One of the indirect effects of growth hormone is protein synthesis. What are proteins made of? Amino acids. In order to make proteins, do you have to have a lot of amino acids or little? Probably a lot. So if you have a lot of amino acids, growth hormone will use them to produce proteins. Does that make sense? Now, we're talking about growth. When do you need growth? When something's broken. Trauma. Make sense? Trauma stimulates growth hormone. Trauma, generally stress. Okay? Because at the moment of stress, you kind of use up your blood glucose a little bit. Exercise. Exercise depletes your energy molecule from the blood. It depletes blood glucose levels. It depletes blood free fatty acid levels. So growth hormone will be produced to compensate for it. Does it make sense? Okay. Now, sleep. Now, this is probably more neurological stimuli rather than metabolic. Do you understand what I'm saying? Like when you sleep, you don't really exercise, you're not stressed, you're fine. But sleep greatly promotes release of growth hormone. So when your mom told you you grow when you sleep, it's true. Okay. Exercise promotes, as you can see here. Okay. Ghrelin. Well, ghrelin is the hormone. It's kind of, I'm not going to ask about ghrelin as a stimulus. Ghrelin is the hormone of hunger. When you're hungry, your blood glucose is low, your blood free fatty acids are low. Ghrelin serves as an additional signal. Does that make sense? What I want you really to focus on are those three metabolic causes. Low blood sugar, low blood free fatty acid, high blood amino acids will stimulate growth hormone release. Do that make sense? In terms of more of a behavioral stimulus, stress, exercise, sleep. Do I make sense? Am I clear? I'm asking you, am I clear for you in what I expect you to know? Good? Therefore, what inhibits? If you just ate the entire cake, okay, you can put fatty acids there too, okay? So if you just had a meal, growth hormone will go down. Does that make sense? That's why, think about this. What is the post-workout meal? Protein, amino acids, right? You throw amino acids, because if you will eat a cake, your blood sugar will go up and immediately quench the growth hormone production. So that's why protein. Obesity. In obesity, you have high free fatty acids in the blood. Aging is probably more of a neurological rather than metabolic cause. And of course, think about this. Exogenous growth hormone. Imagine that I start to inject myself with growth hormone. What effect will it have? And I do it religiously every day, morning and evening. For example, what effect will it have on the IGF levels? They will go up. What effect will it have on the growth hormone levels? Endogenous growth hormone. Decrease, yes. Growth hormone that I produce myself will go down. Does it make sense? The hormone that I'm shooting myself with, it's different story. Does it make sense? So you have to understand that. Okay, we're good? So please know this axis. We will talk about more hormonal axes, and you will be more comfortable with them, and we'll have a chance to review many of them. Now, when we talk about pathologies associated with hormones in general, we always talk about abnormal levels, too high, too low, or lack of hormones at all. In case of growth hormone, another variable that we throw in is when. So deficiency of growth hormone in the childhood leads to the condition known as the pituitary dwarfism. This actor actually has pituitary dwarfism. At the time when skeleton is developing and is growing, lack of growth hormone stunts the growth. Makes sense, right? Now, if the childhood levels of growth hormone are too high, that leads to the condition known as gigantism. Okay? So people with gigantism can be 8-9 feet tall. Fortunately, those patients do not survive for very long. Main cause of this is cardiac abnormalities. So the heart becomes too large, and it's not healthy large. Like you take athlete, they have bigger hearts than regular people, but that heart, that's the normal exercise-induced hypertrophy. Okay, this hypertrophy is induced by growth, so it leads to cardiomyopathy, increased thickness of the ventricular walls, and surprisingly less efficient pumping, decreased cardiac output, and those people usually succumb to condition in late 20s, early 30s. Okay, some people have abnormal levels of growth hormone in adulthood. What do you think can lead to those? Like, person grows normally. Normally, everything's healthy. Then at some point, person starts to show signs of overproduction or underproduction of growth hormone when they are adults. What can lead to that? What do you think? You have to come down to the roots of all evil. Which gland produces growth hormone? Pituitary gland. So if growth hormone levels are off, which organ is probably affected? Which parts? Yeah, which parts? Hypothalamus or pituitary? We technically consider pituitary part of, we talk about pituitary a little bit when we talk about brain. At least it's linked. So, trauma, which gotta be very, very precise trauma, or more common, tumors. Okay, lead to the dysfunction. Now, the lack in adulthood, endocrine abnormalities all across the board. Okay, there's lethargy due to thyroid axis affected. There's obesity because there's no normal breakdown of fat. Loss of sexual function because gonadotropins are not produced. Like, all over the place. Excess of growth hormone in the adulthood leads to the condition known as acromegaly. People with, and you can see the progression of the disease in these pictures. If you can't read the age, 9, 16, well, I can't read the bottom ones either because I just crossed them. 33, 52. So you can see as the person grows, by the age of 16, it's still, there are no very obvious abnormalities, but then you can see bone deformations. The main sites where bone overgrowth manifests, the jaw, mandible, and hands. This condition is not lethal, immediately lethal. Okay, it may lead to cardiovascular problems and metabolic problems, but it is controllable. That makes sense? And it can be, it can work to different extent. Now, since growth hormone promotes growth, can we use it as the performance enhancement drug? I'm not asking should we. I'm asking can we? We can. So, an athletes do it. Of course, it is prohibited. The sad part, studies on athletes that used it versus athletes that did not use it showed no significant improvement in athletic performance in the athletes that used growth hormone. There's no point. But the outcomes, like the side effects, can be pretty devastating. Well, acromegaly would be the first one, right? Obviously. And then, I'm going to talk type 2 diabetes. Why? Exogenous growth hormone may lead to type 2 diabetes. What will overwork the insulin production? What does growth hormone increase in the blood? Glucose levels, which will lead to, as Joseph pointed out, overworking the insulin. So the person will become insulin insensitive, insulin resistant, and that's type 2 diabetes. Just pretty much a constantly elevated blood glucose. Cardiomyopathy. Cardiac overgrowth, not normal overgrowth. Okay. If there is, that may lead, growth hormone may lead to the elevated thickness of the blood vessel walls, and usually it comes at the expense of the vessel lumen. Vessels become narrower, which leads to the hypertension. So, all in all, don't use growth hormones as the performance enhancement drug, if you ever decide to. Okay. Any questions so far? Try not to forget to post a sort of a worksheet today after, either during the break or after the class, so you can kind of practice drawing and, flow charts and things. You good? Moving on. Thyroid. My favorite, honestly, among all endocrine glands, my favorite is pancreas, of course, but we'll get to that. Thyroid gland. Right here. Okay, so it's under the larynx, which is here, anterior to the trachea. It's bilateral, which means it has two lobes, right and left, that are connected by the structure called isthmus. Isthmus, from Greek, isthmus means neck. Okay? It's the largest primary endocrine gland. Good? Now, if you will make a slice of it and put the slice under the microscope, this is what you're going to see. If you had a chance to look at simple cuboidal epithelium in AP1, one of the slides that we use, one of the sample specimens that we use, is the section of thyroid gland. And you might have seen the follicles. And the surface of the follicles, inner surface, are follicular cells. So this follicular simple cuboidal cells. epithelial cells. They produce, well, yeah, they produce thyroid hormone, yeah. They participate in the production, let's put it this way. Okay, they play an important role. We clear about that? And then you may ask, what follicles filled with? It's filled with the colloidal material that is very protein rich. If you want an example of protein rich colloid, can be found in many things. Like take egg. Egg white is the protein colloid. Okay? Just depends which protein is there. In case of the thyroid gland, protein is called thyroglobulin. Thyro, and then globulin thing. Bless you. Does that make sense so far? Another type of cells that, honestly, you gotta be a licensed, board certified pathologist with, I don't know, like a dozen years training under your belt to distinguish those. Another type of cells that you're gonna see in thyroid gland is parafollicular cells. Now, parafollicular cells produce another hormone, calcitonin, which has nothing to do with the thyroid gland function. Now, what's the function of calcitonin? Anyone? Calcium regulation. What does it do to blood levels of calcium? It's like 50-50 question from Jeopardy. So the decrease or increase? Decreases, yes. So high calcium levels stimulate calcitonin. Calcitonin stimulates calcium uptake into the bones. We'll talk about it timely. Okay? We're going to focus on thyroid hormone now. Any questions before we move on to the dreaded part of thyroid hormone, the synthesis of it? So the gland produces 3 hormones: thyroxine, triiodothyronin, and calcitonin. We'll talk about first two first. So these 2 guys are fat-soluble hormones. They are fat-soluble. Therefore, where is the receptor for them? Fat-soluble. Inside of the cell. Okay, the receptor for them is inside of the cell. Calcitonin, on the other hand, is the protein, so it's water-soluble. So this guy has a receptor on the surface. Clear? Good? Now, synthesis of thyroid hormone. I'm not going to ask about, you won't have to write down the entire synthesis. I want you to understand, though, few sort of key points of the synthesis. So, first and foremost, thyroid hormones are produced from the amino acid called tyrosine. Okay, you can see tyrosine right here. Okay. We cool? The inorganic compound that is necessary for thyroid hormone synthesis is iodine. Okay. Has anyone ever seen iodine? Pure iodine. Not the solution, not betadine, pure iodine. It's crystals which are almost insoluble in water. So you cannot transport iodine as iodine in the blood. Instead, iodine exists in the blood in the form of anion, iodide. This one you get with your diet from things like salt, iodized salt. Is that understood so far? So this iodide anion is actively transported into the follicular cell. Okay? Do you follow me so far? From the blood, it is actively transported into the follicular cell. Okay. From the follicular cell, iodide ends up in the follicle, in that empty, well, not empty, colloid filled space inside of the thyroid gland. Iodide is then reduced and finally forms iodine. This I2, iodine, the actual chemical, okay? So this iodine interacts chemically with tyrosine, forming two intermediates. One intermediate has one iodine, another has two. Monoiodotyrosine, diiodotyrosine. Okay. Then they combine. There's some organic chemistry going on. What you end up with is molecule with 3 iodine residues, and eventually molecule with 4 iodine residues. Okay? You follow me? Okay. Now this tyrosine, this amino acid, isn't separate. It's not just floating around. Tyrosine is the part of the protein. Remember I mentioned it? Thyroglobulin. Tyrosine is the part of thyroglobulin. So what you have, think about this. You have, like, I'm thyroglobulin. This is tyrosine, my arm. And now, or whatever, now it has 3 iodines. Okay, so essentially my arm with those 3 iodines, tyrosine with those 3 iodines, it's a thyroid hormone ready to go. The only problem, it is still attached to the protein. Does that make sense? Okay, so protein, thyroglobulin, with thyroid hormone attached, is endocytosed, taken back into the follicular cell, and it is broken down in the lysosome so that thyroid hormone can finally leave the cell and end up in the blood. Does that make sense? So if you try to, essential steps, the ones that I want you to understand. First, we need tyrosine and we need iodine. So iodine is in the form of anion, comes from blood to the follicular cell to the follicle. In the follicle, it becomes iodine, and then via several reaction steps, interacts with tyrosine, blah, 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 interactions, all that kind of stuff. You end up with thyroid hormone, 2 types, either T3, 3 iodines, or T4, 4 iodines. But those thyroid hormones are still attached to the protein called thyroglobulin. Follicular cell takes thyroglobulin inside, breaks it in pieces. Imagine like I'm broken in pieces, like dismembered, and thyroid hormone is now free to go into the blood. Does that make sense? It's all there. It's all recorded. So you can, at your pace, it's just easier. Okay, I understand. I'm not going to give you any formula that you see right there. I'm not going to give you those formulas and ask you, what is this? Don't worry. Don't spend your time memorizing the structures, please. Okay? But I can ask you, in the follicle, is thyroid hormone free or is it attached to the protein? And tell me it is attached to the protein. Okay. What happens to thyroglobulin with attached hormone inside of the follicular cell? It is lysed, destroyed. So thyroid hormone can be released. Does that make sense? So think about those. I want you to focus on those steps rather on the chemistry. Okay. Now, more or less makes sense. Never mentioned what stimulates the production of thyroid hormone. Basically, it's a low basal metabolic rate. Did we talk about metabolic rate at all? Just give me 1 second. I want to check. Yeah, I want to check that I accidentally, I'm afraid to accidentally turn off the mic. No, everything's good. What's basic metabolic rate? Not on the exam. Shoot it out. Or basal metabolic rate. What's that? Go ahead. You don't have to. Yeah, just. How would you measure it? Imagine that you can measure the amount of calories somebody uses. You can. What would you make this person do? Oh no, it's basal. People lay down flat for 24 hours not moving. Seriously, that's how it's measured. You can blink. That's about it. That's your basal metabolic rate. No exercise, nothing. When you exercise, your BMR goes up. I mean, your BMR doesn't go up. Your metabolic rate goes up. It's not basal anymore. Does that make sense? Okay. So basal metabolic rate is essentially your kind of body energy activity. Okay? Right? Correct? One of the great examples of reduced BMR, when you freeze, your BMR goes down. When you get exposed to really cold temperature and you start to freeze, your thyroid hormone levels go up immediately. Okay, and they will send, I hate those comparisons. Overall, they will send your organism into overdrive, meaning they will stimulate energy consumption. Like they will increase cardiac activity. So cardiac output will go up, heart rate will go up, contractility will go up. They will increase utilization of energy. Okay? So if you would look at this, okay? Hypothalamus, pituitary, and thyroid gland form so-called HPT axis. Okay. It all starts with the stimulus. Since thyroid hormone increases BMR, what would be the stimulus for thyroid hormone production? If it increases BMR, what would be the stimulus, initial stimulus? Low BMR, yeah. So you start with the low BMR. Okay. Low metabolic rate. Okay. Low metabolic rate. First and foremost, thyrotropin releasing hormone will be produced in hypothalamus. Through the portal system, it will reach anterior pituitary that will produce thyroid stimulating hormone, TSH, which is the synonym for thyrotropin. Okay? TSH will then act on thyroid gland, stimulate the release of T3 and T4 from the follicular cells into the bloodstream, and you've got Basal metabolic rate elevated. Does that make sense? So BMR goes up. Since your BMR is high, what happens to the release of TRH, thyrotropin releasing hormone from hypothalamus? Huh? See, it stops. Yeah, it decreases. Yeah. Essentially, you have an axis. TRH. Where is it produced? Come on, speak up. What? TRH, not TSH. The first one. Hypothalamus. The next one, yes. That's pituitary, right? TSH acts on the thyroid hormone. On the thyroid gland, sorry, which produces thyroid hormone. And thyroid hormone first will increase BMR. And it will inhibit both TRH and TSH. Does that make sense? This axis that I drew there in blue, does it make sense? Let me tell you, most hormonal axes work same way. Look, if you substitute TRH with growth hormone releasing hormone, TSH with the growth hormone itself, and TH with IGF, that's axis, right? It's all the same type of feedback. Does that make sense? Now, okay, we'll wait. We'll wait till the next portion of info, and you will see how it is regulated in the disease. So normally, again, you have like the whole flow right here. Okay, decreased BMR, elevated TRH from hypothalamus, elevated TSH from anterior pituitary, elevated TH from thyroid, elevated BMR, negative feedback. So TRH and TSH go down. Make sense? Now, it's all very exciting, but what about, well, signaling? Okay. It's fat soluble because of iodines. So it gets inside of the cell. Actually, it gets inside of the nucleus, but no worries about it. I am not focused on like whether it's cytoplasmic or nuclear receptor. You have a lot of on your plate as far as you know that the receptor is inside of the cell because hormone is fat soluble. You're fine. Clear? Hormone binds to the receptor, forms complex, hormone receptor complex. This complex, what does it bind to? DNA. What does it stimulate? Transcription. The product of transcription is not yet. Product of transcription is mRNA, and then mRNA gets into the cytoplasm, to the endoplasmic reticulum, gets translated, and here you got your proteins. This process, does it take time? Oh yes, it does. It takes a lot of time. So these effects of thyroid hormone, these effects are slow. Genomic effects are always slow. Okay. However, interestingly enough, thyroid hormone, it may have some other receptors which mediate non-genomic effects, more direct. So there's no DNA binding, nothing. It does something to like ion channel openings and, second messenger activation, stuff like that. But what I want you to focus your attention when you're learning, when you're preparing for the exam, for instance, is this, hormone receptor is in the cell. Hormone binds to the receptor from the complex. Complex binds to DNA. stimulates transcription, RNA is produced, RNA goes into the endoplasmic reticulum, is translated into proteins, boom, you've got your effect. Cool? Pathologies. First problem, too low. And the most common cause of the hypothyroidism, hypo means too low, so low dietary iodine. First of all, let's just even without looking at the scheme and everything, just think. There's not enough iodine. Is your thyroid gland going to make thyroid hormone? No, it just can't. So, if you don't get enough iodine, the food, your thyroid hormone levels, TH levels, are going to be low. Are we clear? How will it affect the levels of TRH and TSH? So if this guy is low, how will it affect the levels of these two hormones? They're going to go up in order to try and compensate. Does it make sense? Do you understand? So negative feedback will be low. Anterior pituitary will produce a lot of TSH. TSH acts on thyroid gland. Your thyroid gland can't produce thyroid hormone, but I tend to make those things anthropomorphic, but think about, it's sort of, consider it an analogy. Thyroid gland doesn't know that it runs low on iodine. So if each cell cannot produce enough thyroid hormone, maybe if we will produce more cells, it will work. Thyroid gland starts to grow. Does that make sense? That leads to goiter. Okay? It's called endemic or dietary goiter. And people do not have enough iodine in their diet. And this condition is characteristic for third world countries, developing countries. Often people live on, say, rice. Okay, and they just don't have iodine in that rice. Does that make sense? How can you correct this condition? Yes. And interestingly enough, goiter, the increased thyroid gland, will shrink a little. So it will not go back completely to normal, but it will shrink. Okay, now, what would be the overall symptoms of iodine deficiency in relation to the thyroid hormone effects? Think about BMR first, because it's the main. So BMR is going to be low TH means low BMR. Low BMR means you are tired, lethargic, sluggish. Does that make sense? And I like to bring this up when we talk about diseases. We often refer to, oh, this is going to kill you, or you're going to, lose your leg. Something horrible is going to happen. Those people may not die, but their quality of life will be poor. And that will cost them dearly. Does that make sense? Now this is endemic goiter. In autoimmune goiter, also called Graves' disease, sorry, the situation is different. Okay, so this is the generic thyroid gland. Okay, it's not up to scale or up to shape. Just the thyroid gland is an organ. Which pituitary hormone stimulates thyroid gland? Yeah, it's actually right there. Which pituitary hormone? Or immune? You can give me an acronym, it's fine. Huh? TSH, thyroid stimulating hormone. TSH. You got it? Everybody understands that? I'm going to tell you, it's the water-soluble hormone. TSH is the protein. Where is the receptor for TSH? Out on the membranes of the cells of the thyroid gland. Correct? So, for the simplicity, I'm going to put the receptor. Sorry, this thing is not aligned. I will align it during the break. So this is the receptor, okay, for thyroid hormone. So for TSH, okay, that's TSH. So TSH is supposed to bind there and stimulate thyroid, right? We're good? In Graves' disease, patient's immune system produces antibodies which can also bind to the receptor. I'm going to picture them red, okay? And they will compete with normal TSH for the stimulation of thyroid gland. Does that make sense? These antibodies have no relation to your BMR. So what you have, what patient has, is the constant overstimulation of thyroid gland. Does it make sense? This constant overstimulation of thyroid gland that is completely independent of pituitary hypothalamus, how will it affect the level of thyroid hormone? Overstimulation of thyroid gland will increase thyroid hormone. Does it make sense? That's right. When thyroid hormone goes up, how it affects the levels of TSH and TRH. Huh? Yeah, they will be reduced. Exactly, they will be reduced. So in a patient with Graves' disease, if you take blood and you measure levels of those three hormones, what you're going to see? High thyroid hormone, low TSH, low TRH. Does that make sense? Clinical picture. They constantly overproduce thyroid hormone, so they kind of constantly revved up. Okay? Heart rate goes up, so cardiac output goes up, blood pressure goes up. They are excitable. They're like, jumping, bouncing off the walls. Well, not exactly, but they're very active. They're irritable. Okay? I worked with a guy who had this condition, not very major, so it was controlled, but he was irritable, let's put it this way, okay? They also exhibit heat intolerance. Why? When their BMR is revved up, what do they produce? They produce a lot of heat themselves, so they feel comfortable in the cold. If you took classes that are taught by Dr. Landis or Dr. Nussbaum, anyone? No? Well, we have a department joke that they have hyperthyroidism because they have fans. This is too hot for them. Okay? We have a department joke that, when does the spring come? When Dr. Nussbaum starts to wear flip-flops. It's usually like end of February. And summer is when he wears shorts, which is like end of March. So he's healthy, by the way. He's totally healthy. It comes from exercise, not from hormonal abnormalities. But in the person with thyroid overproduction, you will see heat intolerance. Does that make sense? Now, hypothyroidism can be, as we mentioned, dietary. Okay? lack of iodine. Or it can be autoimmune. That's Hashimoto's disease. That's when your immune system attacks the cells of thyroid gland and destroys them. Does it make sense? Sluggish. BMR is low, cardiac output's low. And opposite to heat intolerance, people with hypothyroidism will be cold intolerant. Does that make sense? Because they do not produce enough warmth. They want to be warm all the time. They will develop, maybe not obesity, but, body weight will get elevated because they don't utilize energy as efficiently as healthy people. Pretty much, if you will compare, and that table does it very well, if you will compare the outcomes of hypo versus hyperthyroidism, they're just exact opposite, just perfectly opposite. Okay. Now, understand the outcomes of hyperthyroidism versus hypothyroidism. So if I ask you, what is the possible effect of hyperthyroidism, and I give you a list, you have to recognize. They will, I promise, they will be clear. I'm not going to ask about some murky, protein production or something. High cardiac output, low cardiac output. High blood pressure, low blood pressure. Okay. Irritability, sluggishness, and lethargy. Does that make sense? Interesting feature of hypothyroidism, severe hypothyroidism. It's a condition called myxedema. So that's when thyroid function is practically gone. In this case, due to the biochemical changes, components of extracellular fluid, chondroitin and hyaluronic acid, bind very excessively to the proteins outside of the cells. And they form colloid outside of the cells that will retain a lot of water. And that gel in the interstitium between the cells will lead to the very characteristic edematous appearance, especially in the face. Eyes are baggy, and the face overall is swollen. Does that make sense? That's practically lack of thyroid function. Before we're moving on, any questions? Good? Now we're going to talk about parathyroid gland, and then we're going to take a break, and then we're going to review the quiz. And I'm going to give you another quiz today, so we're going at a pretty good pace. Parathyroid, you've already encountered it in AP1. Okay. It's the gland that regulates calcium. You can find parathyroid gland on the back of your thyroid. So think about, this is thyroid, okay? You flip it, and you see back of thyroid gland and parathyroid glands over here. They're small. Usually there are 4 of them. I mean, if you make a slice and you look inside, it's not really remarkable. You see a bunch of cells, so-called parathyroid cells, or sometimes they're called chief cells. They produce parathyroid hormone. Regulation is probably, one of the easiest. It increases calcium in the blood. So if it increases calcium in the blood, what is the stimulus for parathyroid hormone production? Huh? Low calcium, yeah, low calcium. Low calcium parathyroid hormone produced high calcium. Okay? Low calcium parathyroid hormone produced high calcium. That's it. Now, where can you take calcium? From your bones. Where else? You can. By doing what? It's like money. If you don't have enough money, what you can do? There are three things that you can do. Okay, so you can borrow from your bank account. That's bones. You borrow calcium from your bank account. What else? Well, good idea, but we'll put it in the borrowing part. You pretty technically borrow, just, without consent. Earn more, or nobody likes to talk about the third way. Spend less. Right? Three ways. You borrow, you earn more, you spend less. You have to think about, when we talk about biochemical processes, when we talk about like glucose, fats, anything, and we talk about deficiency and how can you compensate the deficiency, you have to keep in mind, we can get it from somewhere in the body, we can eat more of it, or we can stop excreting it. So, first, bones. Great way. Well, bones are necessary, so it's kind of not great way. Okay? But you can increase the activity of osteoclasts, cells inside of the bone that will break down the bone and release calcium in the circulation. Okay? What's more important? Calcium levels in the blood or bone integrity? Calcium levels in the blood. Nobody cares about the bones. Okay? Calcium levels in the blood are absolutely critical. How can you get more calcium in? Food, yeah, food. It's not a problem, but if you will start munching on chalk, it's not going to really help. Or if you will consume 2 gallons of milk a day, all it's going to give you is profuse diarrhea. Believe me, I tried. You need not only getting calcium in the system, you got to get calcium from the intestines into the blood. That's parathyroid hormone. It will increase, it will increase absorption in a small intestine. Not directly. It needs vitamin D for it. Okay? It's like vitamin D. Where is it produced? Skin. When you expose yourself to the sunlight, then it has to be activated by kidneys. Then it will increase the calcium absorption. Kidney activation involves parathyroid hormone. Speaking of excretion, how do you excrete ions? Kidneys. Okay, that's your main site of ion excretion. So parathyroid hormone reduces excretion of calcium. This picture says calcium reabsorption. Pretty much you filter calcium out of the blood and then you take it back. The more you take it back, the higher calcium levels in the blood are going to be. Okay? Does that make sense? So I have 3 main sites. Bones, borrowing, reabsorbing calcium in kidneys, that's spending less, and earning more, getting more calcium from the intestines into the blood. Does that make sense? Perfect. Another hormone is calcitonin. Which gland produces calcitonin? We just discussed it. Huh? Not parathyroid. Just discussed it. Thyroid. Thyroid makes calcitonin. Okay? So, parafollicular cells make calcitonin. Calcitonin will increase deposition of calcium in the bones. So that flow chart kind of explains it. Okay, so low blood calcium, parathyroid hormone activates mechanisms to increase blood calcium, either intestinal, kidneys, or bone. Calcium levels increase. If they increase too much, calcitonin kicks in, leads to the deposition of calcium in the bones. Okay. Now this is kind of an interesting graph right here. So on the y-axis, sorry, on x-axis, it's the concentration of calcium in the plasma. Can you see on the bottom? Here's your normal, about 9.5. On y-axis, on the left, concentrations of parathyroid hormone, it's red. Here, concentrations of calcitonin. So you can see even small changes in blood calcium. Let's talk about calcitonin first. Look at this. Even small change, like you go from 9.5 to 11. Oh, sorry, that's, okay, 12, okay? Your calcitonin just shoots up right away. Does that make sense? Can you see that? You go low, your parathyroid shoots up right away. That shows you, first and foremost, that calcium concentration in the blood is critically important to be maintained at a very tight level. Second interesting thing, you see this dashed line? This dashed line represents the level of parathyroid hormone, not in the acute calcium decrease, but in the chronic. So imagine someone has a nutritional calcium deficiency. Okay, person doesn't consume enough milk or any broccoli, any calcium-containing products. Does that make sense? Calcium levels are not very, very low. They just that bit low. If they are a little low, how will it change the levels of parathyroid hormone? Don't focus on a bit. If calcium levels are low, what's going to happen to PTH levels? They're going to increase, but not too much. But look, the problem is there's not enough calcium in the diet. So your calcium is still subpar. Parathyroid gland will try to compensate for it, increasing. If this much doesn't work, let me throw more. If more doesn't work, let me throw even more. If even more doesn't work, let me throw even more. Does that make sense? So if someone experiences chronic mild hypocalcemia, it will lead to the huge increase in parathyroid hormone production. Your bones will go to trash. Now, why calcium is so important? Hypocalcemia impairs the regulation of the muscular activity. Okay? Leads to the sustained contractions, twitching, spasms. One of the characteristic appearances of hypocalcemia is the green, when a patient has the permanent contracture of the facial muscles, something like this. Okay? Smile. And usually this smile, one of the ways to treat it, if it's just a seizure, muscle seizure, you can slap, it will go away. Slap doesn't do anything. Okay? And eventually, if it's disseminated hypocalcemia, diaphragm goes into the contracture, and that's respiratory arrest. Hypercalcemia will lead to the muscle weakness. In severe cases, it may affect performance of the cardiac muscle, depression of nervous activity, constipation, but the first and foremost, kidney stones. So you can see, having too much calcium or too little calcium, both is bad. And what I want you to very clearly understand here, which is honestly, come on, it's very simple. PTH increases calcium levels in the blood. Calcitonin decreases it. PTH comes from the parathyroid or chief cells. In a parathyroid gland, calcitonin comes from parafollicular cells in the thyroid gland. And for PTH, I will ask you about the mechanisms. On the level of osteoclast activation, decreased renal excretion, or increased renal reabsorption. Pretty much, you can say less calcium goes away with urine. And in the intestines, increased calcium absorption from food. But for this, you need vitamin D. We cool? Let's take a break. And when we come back, we will review the quiz.